In this section, we're going to learn a little bit more about our estimators. So one of our main goals in statistics is to use our sample statistics to estimate our population parameters. But we need to make sure that our statistics are good estimators. So we're going to use our sample mean x bar to estimate our population mean mu. Or we could use a sample proportion to estimate a population proportion. But how do we know that our sample mean is actually our best estimate of our population mean? This isn't something we take for granted. We can actually prove this in statistics. Okay, the way that we know it's the best estimate is because we know that if we found thousands and thousands or infinitely many different sample means from different samples, that the average, or instead of average, the expected value of all of those sample means is going to be equal to the population mean. Okay. And we proved this in a previous section, so we know that the expected value of our sample means, of all of those possible sample means, is equal to our population mean. Or if you wanted to look at it visually, this is the sampling distribution of x bar. These are all the possible sample means. So all the possible sample means x bar. And in the center is our population mean mu. What that means is that on average, our estimates aren't overestimating or underestimating the population mean, because that would be bad if we knew they were always overestimating or always underestimating it. So the sample mean is an unbiased estimated population mean. Now, if our estimates had been consistently over or consistently under the population parameter, then we'd say that our estimate was biased, and we don't want something to be biased. Okay. So when you look at it, yes, when I get all these sample means, I might get a sample mean that's equal to my population mean, like right here. But I might also get a sample mean over here that's a bit too high. I might even get a sample mean that's really, really too high, but I might also get one that's really low. And it's the fact that some are high, some are low, but they're all centered around the actual population mean. That's what makes it unbiased. We also want to make sure that our estimate has a low variance in the sampling distribution so that we get good estimates. Okay. So we're talking about the variance right here. How much variation is there in all those possible sample means? We want that variation to be pretty small. Okay. We don't want to have a really wide range of guesses for our sample mean. So for our sample mean, we would expect our sample mean to be about what? Okay. So if you remember, expected value of x bar is equal to mu, and the standard deviation of x bar is equal to sigma over the square root of n. So when we take a sample, we would expect our sample mean to be about equal to our population mean mu, give or take sigma over the square root of n. So I can tell you in advance how close your estimate will probably be. Okay, and now here's an important part. Statisticians have proved that our sample mean has the lowest possible variance of any possible statistic that anyone could have possibly thought of to actually estimate the population mean. So we know that our sample mean is a good estimate. Now I want you to visualize this so that you can see why we want to have low bias and low variance. So let's see, or pretend that trying to estimate a population parameter is like being in a shooting contest. Which method gives you the best estimates? So you can see, let's start with a bad example, like right here. The points are all kind of centered on the target. They have low bias. They're centered around the bullseye where they're supposed to be. But the variance is really high, so they're not really close to the bullseye. Versus right here, okay, we're centered on the target where we're supposed to be. It has a very low bias, and the variance is also really low. So all of those estimates would be really close to the real value. But if we come down here, notice that I have a really low variance again. My points are tightly clustered, okay, but I'm not even close to the bullseye. So I have a high bias and low variance. And for this last one, I'm not close to the bullseye, so I have a high bias, and my points are really spread out, so it's also a high variance. Okay, so we want to have an estimate with a low bias, or no bias, and a low variance. And so anytime we do any estimation in statistics, someone says, well, what if we use this to estimate something? They have to go through and say, does it have low bias? Does it have low variance? Before someone else is going to want to use it. So we're going to call something a point estimate if it's a statistic that represents our best guess of the value of a population parameter. It's called a point estimate because it's just like one number. Okay. And there might be more than one good point estimate. Statisticians have come up with lots of different procedures, lots of different ways to estimate things. An estimate is unbiased if the expected value of the statistic is equal to the population parameter that it's supposed to be estimating. Otherwise, we'll call it biased. And we want unbiased estimates. We also want estimates with the smallest variance in their sampling distribution. So in this example, suppose that each of these curves shows a possible distribution of an estimator of the parameter theta. What does each image tell you about the possible values of the estimator? Now theta, we just picked a random Greek letter to say it's some parameter. We don't even care if it's the mean or proportion, just any parameter. Okay. Which of these images would be the best estimating? Okay, so when you look at A, it looks like it's centered at the parameter, so A is unbiased. If we look at B, notice theta is way over here, but most of the B estimates are over here, so it's definitely biased. It's not centered at the parameter. It's always going to be overestimating. Okay, C looks like it's centered at the parameter, so it is unbiased. Okay, so we have to choose between A and C. They're both unbiased, but notice C has a lower variance. So C is the best option. Now, with our formulas that we learned for discrete random variables, we can prove, we're not going to do it here, but we could prove that the expected value of our sample proportion p hat is equal to our population proportion p. And the standard deviation of our sample proportion is equal to the square root of p times 1 minus p all over n. So the question is p hat an unbiased estimator of p? Okay, yes, because the expected value of p hat is equal to my population parameter. Okay, so it's unbiased. If we use p hat to estimate p, how much are we likely to be off by? We're likely to be off by the standard deviation. So the standard deviation of p hat, that's how much we're likely to be off by. Or in this case, the square root of p times 1 minus p over n. Now, because that standard deviation p hat tells us how much our estimate is likely off by, we have a new name for it called standard error. We can say that the standard error of p hat is equal to that square root of p times 1 minus p over n. Notice, this is exactly the same thing as the standard deviation of p hat. So this is the standard deviation of p hat is equal to standard error of p hat. It's just a new name to remind us that we're estimating and it's how much we're likely off by. It is not something new, it's just a nice name. So here's some common unbiased estimators. Each of these statistics is an unbiased estimator of the population parameter. So our sample proportion p hat estimates our population proportion p. Sample mean x bar estimates our population mean mu. And our sample variance s squared estimates our population variance sigma squared. Now, if you remember, back when we first learned about variance, we talked about the two different formulas, okay? And the reason that we had to have different formulas for our population variance versus our sample variance is because it makes our sample variance an unbiased estimator of the population variance. There are proofs you can do in the graduate level class to show why this makes it unbiased. So this sigma squared, that's our population variance. And remember, we divided by n, the population size. But for our sample variance, we had to divide by this n minus 1. So that's for our sample variance. And it's just because then it becomes unbiased. So we mentioned the new name of standard error. That's how much our estimate is likely to be off by. It's just the fancy name for the standard deviation of our sampling distribution for our estimate. So like the standard error for x bar is just equal to standard deviation of x bar, and that's sigma over the square root of n. Now we know that our sampling distributions for both our sample mean and sample proportion are approximately normal for large sample sizes. So we can apply the empirical rule to our estimates. So we look at this image, I don't know if you remember, if we have our parameter here in the middle, if we go up or down one standard deviation, but now we're going to call it a standard error to remind ourselves that we're estimating. If we go up or down one standard error, that should include about 68% of our possible values. Or we could say 68% of the time our estimate is within one standard error of the population parameter. 95% of the time the estimate is within two standard errors of the parameter. And 99.7% of the time is going to be within 3 standard errors. So this is our 68%. If we go out to 2 standard errors, we're at 95%. And if we go out to 3 standard errors, then we're at 99.7%. Okay. And so that's the actual parameter, and 95% of all of our possible sample statistics for our sample means or sample proportions will be within 2 standard errors of the parameter we were trying to estimate. And again, standard error, it's just the fancy name. It's not something new, okay? It's the standard deviation of that sampling distribution of the possible values we could get. So now let's talk about what happens if we have to estimate our standard error. So here's my problem. If we want to estimate our population proportion P, so to remind ourselves, that's our population proportion. That means that we don't know what the population proportion P is. So how are you going to calculate the standard error of P hat? Because the standard error of P hat, or the standard deviation of P hat, is equal to P times 1 minus P over N, and then take the square root. But I don't know what P is, so I can't tell you what the standard error is. So what we have to do is, because we don't know that population parameter, we have to use our statistics to estimate the standard error of the statistic. Okay, we're kind of getting stuck in a loop here. So the standard error of our sample mean, instead of saying, so it's supposed to be sigma over the square root of n, but we don't know what sigma is, this population standard deviation, so we'll estimate it with our sample standard deviation. Okay, and for the standard error of P hat, we don't know what P is, so we're going to do a P hat times 1 minus P hat over n. Okay, we'll do use our sample proportions instead of our population proportions. So let's try an example about long COVID. Long COVID has a wide range of symptoms that can last for months after you're infected. Common symptoms include fatigue, difficulty breathing, headache. A report back in 2022 said the proportion of U.S. adults who had long COVID symptoms was 0.075, and the sample size was 62,000. So now, what was the parameter of interest? So when you look at this, they said the proportion of U.S. adults, but they also gave us a sample size. So this was actually my sample proportion. They didn't actually look at all U.S. adults because that's millions of people and that would have taken too long. So the parameter of interest would have been the proportion of all U.S. adults that had long COVID. Let's see, yeah, sorry. All U.S. adults with long COVID, which would be P. Now, what is our point estimate of the parameter? Well, it's that sample proportion, which they said was 0.075. Now, what is our standard error? So the standard error for P hat, it should have been equal to the square root of P times 1 minus P over N. But we don't know what our population P is. So I'm going to estimate that by the square root of P hat times 1 minus P hat over N. So this is going to be our P hat is 0.075. We'll do 1 minus 0.075 divided by N, which is 62,157. So 0.00105. So our best guess for the proportion of all the U.S. adults who had long COVID is about 0.075, so that's my actual sample proportion. But we're likely off by about 0.00105. So we're likely off by about 1 standard error. And our estimate should be within, let's do 2 standard errors here. So we know, so this was 1 standard error or 1 standard deviation. We know that 68% of all of our sample proportions are going to be within that 1 standard error, but we know that 95% will be within 2 standard errors of the true population proportion. And 2 times my standard error, that was 2 times the 0.00105, gives me 0.0021. Okay. So we're likely off by about 1 standard error, and we should be within that 2 standard errors for sure. So for our next example, we took a sample of 6 students at USU, so that's going to be a sample size of 6. Found that the mean height was 71. That sounds like it was for the sample, not the population, so my x bar equals 71. The sample standard deviation was 5.39, so S equals 5.39. So what's my estimate of the true population mean height for all the USU students at USU? So we want to estimate my population mean, mu, and my best estimate is my sample mean x bar of 71. Okay. Now what's my standard error? My standard error of my sample mean is going to be equal to, well, it should be standard population standard deviation over the square root of n. But I don't know the population standard deviation, so we can estimate that with my sample standard deviation over the square root of n. So my sample standard deviation is 5.39, And my sample size was 6, so we have 5.39 over the square root of 6, which is about 2.2. So my estimate is likely to be how close to the true value? So likely be within 2.2 of the true value. So likely within 1 standard error. In this example, a sample of employees at a company have the salaries in thousands of dollars. We have 65,000, 92,000, etc. Okay, so we have this list of data. I'm going to first put it into R and find my summary statistics. Okay. So I'm going to enter in R as a vector. Okay, we're saying we're making a vector. We're using C for combine all of these values. Then I'm going to ask for the mean of it, the standard deviation, and the length. The length will tell me the sample size. Okay, so when I come into R, as I run the line of code to create the vector, you'll see the vector show up over here. You can see it's a numeric vector, and there are 10 values. When I do the mean, we see the mean is 67.8, the standard deviation is 24.8, and the length is 10. So that length gives me the sample size. So let's go write those down. So I mean x bar equals 67.8. My sample standard deviation is 24.8. And my length, my sample size is 10. Okay. So now let's see what it wants me to find. Let's find the point estimate for the mean salary of all the employees of the company. So we want to estimate our population mean, mu. So our estimate is x bar equals 67.8. That's my best estimate. Let's find the standard error. So my standard error for x bar is, well, it would be equal to my population standard deviation sigma over the square root of n, but I don't know the population standard deviation, so I have to do the sample standard deviation. And if you want to be fancy, we say it's approximate instead of actually equal. So my sample standard deviation was 24.8 over, and then over the square root of the sample size, so divide by the square root of 10. So 7.84. So our best estimate of the population mean salary was our sample mean of 67.8, and we're likely off by about 1 standard error, so about 7.84. Now, as a separate question, let's see what happens. Let's find the point estimate of the proportion of the company employees with salaries under 70,000. Okay. Now, there are ways to do this in R. I'm just going to count them up though, because it'll be simpler. So if we count them up, we have 65, the 34, the 72, no, not 72, the 40, the 55, and the 41. So there are 1, 2, 3, 4, 5 values out of 10 that had salaries under 70,000. So I'd say that p hat equals 5 divided by the 10 total, so 0.5. Now we need to find the standard error for that estimate of the proportion. So we're looking for now for the standard error of p hat. And that's equal to the square root of p times 1 minus p over n. But we don't know the population proportion. That's what we're trying to estimate. So we'll have to estimate that with the square root, and we'll do p hat times 1 minus p hat over n. So that's going to be the square root. We're going to do 0.5 times 1 minus 0.5 divided by my sample size of 10. So 0.158. So our best estimate of the population proportion with salaries under 70,000 is 0.5, give or take 0.158. So it's very useful when we know we want to go take an estimate to know how close our estimate probably is to the true value. So one more example here. Suppose a researcher chooses a simple random sample of American adults and asks them whether they would have children if they could do life over. What's the probability that the sample proportion they get is within 1 standard error of the actual population proportion? Well, remember our little drawing. When we take, so this is the sampling distribution. Let's draw the sampling distribution of my possible sample proportions. So all my possible sample proportions should be centered at my population proportion P. This is my actual one. So my actual population proportion. whatever sample proportion I get should be centered there. And if we go out one standard error, either above or below, okay, then that should be 68% of all the possible sample proportions should be within one standard error. Okay. So what's the probability that they get a sample proportion within one standard error of the true value? 68%. Okay. And what's the probability that they get a sample proportion within two standard errors? Well, if we want to go out two standard errors, above or below, okay, then that's going to be 95%. So we'll say 95% there. That's reassuring. It tells us we can tell someone in advance, if you want to go take a sample proportion, you have about a 68% chance that you'll get a sample proportion within one standard error. And you have a 95% chance that you'll get a sample proportion within two standard errors. Okay. Just in summary, so that you can come back and reference it easily. Remember, our standard error is just a fancy new name for the standard deviation of our estimate. Okay, it reminds us that the standard error is how much we're likely off by. So the standard of p hat is just equal to standard deviation of p hat. Okay, and there's your formula. We've been using these formulas for a little while. But if we don't know the population values, we have to estimate to get our standard error, which is what we have here.